The objectives for this video are to understand the concept of the p-value and to learn how to use the p-value in hypothesis testing. The hypotheses stated here indicate a right-tailed hypothesis test about a hypothesized mean mu sub 0. The graph shows us the rejection region to the right of the critical value and the region to the left of the critical value where the null hypothesis would not be rejected. Alpha is the area in the tail of the distribution outside of the critical value. It is the probability of committing a type 1 error, which is to reject a true null hypothesis. So alpha is the area under the curve that is shaded in green. When a test value is calculated in a hypothesis test, there are two possible cases. Either the test value lands in the rejection region, or the test value lands in the region where we do not reject the null hypothesis. First, let's look at the case where the test value lands in the rejection region. Since the test value is in the rejection region, we should reject the null hypothesis. The p-value is the area in the tail of the distribution outside of the test value. So the p-value is the area under the curve shaded in red. Note that this area shaded in red is smaller than the area shaded in green. So therefore, the p-value is less than alpha. Now let's look at the second case, where the test value lands in the region where we do not reject the null hypothesis. Since the test value is not in the rejection region, we should not reject the null hypothesis. Remember that the p-value is the area in the tail of the distribution outside of the test value. So the p-value is the area under the curve, again shaded in red. Note this time that this area shaded in red is larger than the area shaded in green. So this time the p-value is greater than alpha. The decision rule when using a p-value is, if the p-value is less than or equal to alpha, reject the null hypothesis. If the p-value is greater than alpha, do not reject the null hypothesis. Now let's look at a left-tailed test where the alternative hypothesis states that the population mean is less than some hypothesized value. The graph indicates to us that in this particular instance, the test value has landed in the rejection region. Remember that the p-value is the area in the tail of the distribution outside of the test value, and again is the area under the curve shaded in red. In this instance, then, the p-value is less than alpha. So our decision should be to reject the null hypothesis. Here is another instance of a left-tailed test. This time, the test value lands in the region where we do not reject the null hypothesis. Again, the p-value is the area in the tail of the distribution outside of the test value shaded in red. In this instance, the p-value is greater than alpha. So our decision should be to not reject the null hypothesis. We can also use the p-value to make decisions in two-tailed tests. In this particular instance of a two-tailed test, the test value has landed in the rejection region. The p-value is the sum of the two symmetric areas under the curve shaded in red. In a two-tailed test, alpha is split into the two tails and is therefore the sum of the two symmetric areas shaded in green. The graph shows the sum of the two areas shaded in red is smaller than the sum of the two areas shaded in green. So the p-value is less than alpha. So our decision should be to reject the null hypothesis. In this video, we worked to understand the concept of the p-value and learned how to use the p-value in hypothesis testing.